Hi everyone, in this lecture I'm going to talk to you about how the light from the sun interacts with our atmosphere. I hope you enjoy this lecture. It's going to kind of connect a lot of the dots from the ozone chapter to this chapter. Okay, let's get started. So first of all, just as a reminder, okay, we have sunlight that hits our earth and gets into our atmosphere, which is a little circle here. And the light that we're looking at is pretty much our infrared radiation, or IR. You'll call it IR a lot in this lecture, and your UV radiation. So IR radiation, UV radiation, and our visible light. All right, here's a nice cartoon of what happens. So here's the sun. It shines a UVA, UVB, UVC light, and about 8% of the sun's radiation is ultraviolet. Remember, UVC were the dangerous UV rays, but most of it, pretty much 100%, gets absorbed by the atmosphere, and about 95% of UVB rays get absorbed, and most of UVA actually hits the surface of the earth. Only 5% get absorbed by our atmosphere. Now if we look at visible light is about 39% of the sun's radiation. And finally we get to infrared. And infrared is about 59% of the sun's radiation. Now when this radiation, the infrared, hits the earth, right, some of it does get reflected. Remember, that's what warms up our earth, is that infrared radiation. And what if you look down at the earth itself, here's another cartoon of that. You have the infrared radiation hitting the earth, and also you have your UV rays, right? So you have infrared, UV rays, and visible light all hitting the earth. Okay? And that warms up the surface of the earth. Okay, and as it warms the surface of the earth, its infrared radiation is actually emitted. And what happens, that means our planet stays warm, okay, but some of it does get back out into space. Remember, it doesn't all stay on Earth or within our atmosphere, or we would just be too hot. Our planet would just be too hot. So the question for you is, why is CO2, or carbon dioxide, a greenhouse gas, this linear molecule here? Why is it? The simple answer, it absorbs infrared radiation and traps heat near the surface of the earth. Now the next question for you is, how does that happen? To understand how it happens, you first have to understand electronegativity. Electronegativity is a measure of the ability of an atom to attract electrons in a covalent bond. Another way to think of it is it's an atom that likes to take all the electrons. It's an electron hog. And so if you were to look at hydrogen chloride, chloride likes electrons much more than hydrogen. So it's going to have a partial negative charge. Notice it's not a negative charge, it's a partial negative. And the hydrogen would then have a partial positive. And that's just because there's a larger electron cloud around chlorine. And if you were to look at the Lewis structure, that would make sense. The chlorine has an octet, so it would have 8 electrons surrounding it, while hydrogen would only have 2. So you would expect the chlorine to have a larger electronegativity and a larger partial negative charge. There's actually a chart you could look up to see which atoms are more electronegative. But if you were to look at the chart, the one at the very furthest right, all the way at the top, and that's the trend right to the top, has the largest electronegativity. That's fluorine. And as you go down, it decreases. So oxygen is more electronegative than carbon. So here's our carbon dioxide again. Remember, we just looked it up. Oxygen's more electronegative. Carbon would then be, have that partial positive charge. And notice that the carbon dioxide has 2 electron groups for the central atom, and that would make it linear. And your main thing I want you to notice here is your dipole moments. Nice, huh? Okay, you can actually represent dipole moments with a vector. So the arrow would point towards the more electronegative atom. So you can either do negative partial negatives or vectors, same thing. But the dipole moment, or dipole, means the molecule is polarized with negatively and positively charged regions. That's the key here, you guys. That's the key. You have to have a dipole for anything to happen with infrared radiation. So the question for you now again is, what happens when IR light hits a molecule? We can have water, hydrogen, oxygen, carbon dioxide. The answer is it depends. Okay, I'm going to show you this really great video clip about asymmetrical, symmetrical stretching and bending. Okay, so let's go ahead and get started.
Must have a moving dipole when it vibrates. The IB wants you to know about two sorts of molecule. The first one here could be water or sulfur dioxide or even CH2, part of a larger organic molecule. All three of these vibrational modes, symmetrical stretching, asymmetrical stretching and bending, move the dipole. And if the dipole moves, then this will be infrared active. You can see it on an IR spectrometer. Now for clarity's sake, the red ball does actually move a little bit, but I've not shown the motion just to make it clearer. But I will show it in the next one. The IB doesn't really care about it though. So this is carbon dioxide, and there are also three different vibrational modes you need to know about. Not all of these involve a shifting dipole. The one on the left, the symmetrical stretching, the dipole is not moving. The asymmetrical stretching and the bending, the dipole is moving. And if you look closely, the little carbon in the middle is also slightly shifting as well. Now the IB don't.
Okay, so that was a really great demonstration of how this stretching and bending works. So the key term you need to remember is if the dipole changes. So if the dipole changes, then it can be IR active. So here is an infrared spectrum for carbon dioxide. You'll notice there are two peaks here. On the y-axis is percent transmittance, and on the x-axis here is the wavelength. And the wavelength is just the inverse of the wave number. Alright, so the first peak you see here, okay, is for the stretching. And this is only for your asymmetrical stretching. Notice here is your carbon dioxide, so carbon's in the center, one oxygen is moving outwards and the other oxygen is moving inwards. So this is your asymmetrical stretch, so your dipole moment is changing. So therefore you get an absorption here. And this is your bending. Okay, this is a picture to these two pictures represent actually one movement. Alright, but this is that one where you see the molecule going up and down, up and down. Again, you see a peak here to indicate that that is infrared active. Notice that you do not see the symmetrical stretching, where the two oxygens are going out at the same direction, not the same direction, but they're both going outwards, so they balance each other out. This molecule, or this version, is not infrared active. Okay, let's skip that. So my question for you is now, what about hydrogen and oxygen? Would you expect hydrogen and oxygen to be infrared active or not active? Well, I hope you had a moment to think about it, but you would expect it actually not to be active. It would look something like this, where you would actually, the stretching for hydrogen would be symmetrical. And same thing for oxygen, it would be symmetrical. You would not have any of these bending or asymmetrical stretching. You don't have three molecules or three atoms anyway. So you would not expect oxygen or hydrogen to be infrared active. So what does that mean? It's not absorbing infrared light. What does that mean? Hydrogen and oxygen you would not expect to be greenhouse gases. Your greenhouse gases have to absorb the light, the infrared light. So just as a summary of your molecular responses to different types of radiation, we've already talked about UV during ozone chapter. And remember, UV is a higher energy than infrared. So when the UV light hits a molecule, if it's high enough energy, it will break it up. Just like you saw with the ozone. Remember how ozone is split up by the UV rays? And as you go down to lower energy, the infrared light can actually make your molecules vibrate. And if it's asymmetrical, right, and it's infrared active, it will absorb that heat or that light and keep the climate or the earth warmer. While with hydrogen or oxygen, the infrared would just pass right through it. Now, if you go further down in energy to microwaves, actually the microwaves make your molecules rotate. And that's part of the reason why they make your food, or that's the reason why they make your food warm up so fast, because it's making your molecules vibrate or rotate rapidly. And as you go lower and lower down in energy, you don't get really any effects on the molecules, such as radio waves. It's not really affecting your molecules in your body as they pass through you. All right. Well, I hope that explains why carbon dioxide and even water is considered a greenhouse gas. They absorb infrared radiation, and other gases such as hydrogen and oxygen do not. And that has everything to do with their dipole moments. All right, I will see you guys next week. Okay, bye-bye.